All right, Bismillahirrahmanirrahim. Let's start problem F8-3, okay, of your RC Hibler book 12th edition, okay. It's a fundamental problem. And what does it says? Determine the maximum force P that can be applied without causing the 250 kg crates to move. The coefficient of static friction between each crate and the ground is mu s equals to 0.25. So this is what he's asking us, and he says you need to calculate the maximum force P. Okay, so which means where is the this he is asking you about this force. Okay, this force he wants to asking you, but this force needs to be maximum, but did not create a movement or slippage in the system. So if you look at it, this unique force will never be lying in this portion of graph. In this portion of graph, it will never be lying on this axis. If you look at it, this force will always be lying, because this force has to be the maximum. This force has been to be a maximum. So if this force is maximum, so if you look at from this graph, the maximum position of this graph is only 1, and this is going to be the maximum, where your at this position the friction, the static friction will be maximum, and where it is maximum, this P will also be maximum, because it is F is equals to P. He says F is equals to P. So if you look at it, can we solve this problem directly? If you want, you can say basically, if you look at this is the free body diagram, okay, the entire free body diagram. The weight is acting downwards for this is A, okay, this is very important, this is A. So this is the A. The weight is acting downwards of this crate, if you look at it, and the normal direction is up. When this force is going to move, because of its effective component of this, the effective component of this force, if you look at it, what will be the effective component of this force? If you say, the effective component will only be this one. This is the component P cos 30. So effective component will be P cos 30, and because of which it's going to move in this direction. So the frictional force is going to be in which direction? The frictional force will be coming in this direction. This is the frictional force. This is our frictional force. Okay. So if you look at it, and other ways, so you can see there are how many unknowns. If you look at it, how many unknowns are there? 1, 2, 3. So you have got how many for this A? How many you got? 3 altogether. Your unknowns are 3 unknowns. Okay, and if you look at it over here also, this is 1, 2, 3 as a system, and if you look at it in B here, 1, 2, 3, 1, 2. Sorry, this is 1, 2, and 3. So these are 1, 2, 3. So again, if you look at it, there are 3 unknowns: NB, FB, and P. Here the unknowns were Na, Fa. These were the unknowns Na, Fa, and T. Here the unknowns were NB, FB, and P. These 3 unknowns. As a whole, if you look at it on as a whole, on this basically 250 kg crate, you have how many equations of equilibrium to solve this? So equations of equilibrium is equals to 3. So basically it means equations of equilibrium is equals to 3, and unknowns on this system is 6. So what does it mean? It means it's basically what kind of, you have got less equilibrium equations, more unknowns. So it is what does it says? It tells observation. So what is going to be your observation? If you look at observation, will be it is a statically statically indeterminate problem. Indeterminate problem. Okay, so this was, we're talking about this as a whole system. This as a whole system. If you look at this as a whole system, okay, so this is a statically indeterminate problem. How to solve this? This is the real question. Now this is being done. We agree with this, we agree with this, we agree with this, we agree with this, and we also agree that it is a statically indeterminate problem. All these things are basically being agreed upon. So what to do? What else we can do about it? Okay. Now we will say, since it is a statically indeterminate problem, we will try to break it up into, for our ease we'll break it from, basically what we'll do, we'll break it, we will consider this as our A. Okay, free body diagram A. Okay, so if you look at it, this is the normal direction, this is the friction, this is the weight, and you can also break it down from here also. You can also, if you look at it, we can break it from here also. We can break it from here also. Okay, we can break it from here. So when we break it from here, we are basically going to get basically this is going to be normal reaction. Basically at A, this is the frictional component, and again when we basically cut it from here, we, in this cable we will have this tension force. But before that, we have to decide whether it is your type 1 problem or type 2 problem. Type 1 or 2. Okay, it is type 1 or type 2, we have to decide. So if you look at it here, basically how many basically unknowns they have given you basically. And again, one more thing, if you look at it, no dimensions are given. Very important point, no dimensions, no dimensions, no dimensions, which means x cannot be calculated. X is basically, what is basically x? You remember that x from theory, from Hebler theory, x from Hebler theory cannot be calculated, cannot be calculated, it cannot be calculated. So moments cannot be applied, so moments cannot be applied, cannot be applied. Okay, so if this is the scenario, so now we have basically actually how many equilibrium equations that you can apply over here. In the case 1, you will have basically, since moments cannot be applied, so we can easily deduce that this is all correct. Okay, so now we will say if you look at it, moments cannot be applied, so it means that you have, when considering this scenario, you will have sigma fx equals to 0, sigma fy equals to 0. These are your equations of equilibrium. Okay, So if you look at it here, this is the equilibrium equations that you will have. And okay, if you look at it, and in the same way, if you look at this system also, you will have again equilibrium equations of equilibrium is equals to, again it will be 2. Okay, so if you look at it, how many equilibrium equations do you have in this system? You will have, if you look at it, you will have 4 equations of equilibrium. Okay, you have 4 equations of equilibrium. You have basically 4 equations of equilibrium. Now basically, if you have 4 equations of equilibrium here, and if you look at it, how many friction equations that you can apply? One friction equation can be applied here, and one friction equation can be applied here. So you can again say basically you will have 2 friction, one here and one here. So friction equations are 2. So it means that equations of equilibrium will be 4, 2, and again over here if you look at it, this is also going to be 2. Okay, so 2 plus 2 is equal to 4. 2 plus 2 is equals to 4. So 4 equilibrium equations and 2 friction equations. So what does it mean? It means that and how many unknowns do you have in this system? Okay, how many unknowns do you have? If you look at it, 1, 2, 3, 4, 5, 6. Okay, so if you look at this thing over here, or if you look at this thing here, you have this equation, unknowns is equals to equilibrium equations plus frictional equations. So if you look at it, how many equilibrium equations you have? 4, plus how many friction equations you have? 2. How many unknowns do you have? How many unknowns do you have? If you look at it, unknowns you have completely 3 plus 3, which is equal to 6. So it means this is 6 and 4 plus 2 is 6. So this means this problem is going to be a type 2 problem. This problem is in which type 2 problem. It is going to be a type, if you look at it, it's going to be a type 2 problem. This is a type 2 problem, and in type 2 problem you are allowed, okay, this equation can be used, okay, can be used during the solution. You are allowed to use f equals to mu n, because he says this point P is actually acting over here. Okay, so you are basically here because if you look at it, your f max, this is your f max equals to mu s into n. So you are allowed to use this point. And this is, what is this actually? This point is called, this is the impending motion. Okay, this is the impending motion point. Okay, so once this has been done, how shall we proceed? It's very simple from now on. Okay, if you will take this block A, the plate A, okay, so just apply sigma Fy. If you apply sigma Fy over here, it means all the forces about the y-axis. This is Na, this is Na, the weight is acting on the negative y, okay, because you know this is, if you look at it, this is your x, positive x, and this is your, if you look at it, this will be your, this is your, this is your positive y. Okay, this is your positive y. So we can say Na minus W equal to 0. Okay, but what is W? W is given as, they have given us the weight as 50 kilogram. 50 into 9.81 is basically 490 Newton. So now you have calculated basically your Na. You have calculated your Na. Now what you do, since Na is calculated and you are allowed to use the friction equation. So you can use Fa equals to mu s into Na. Mu s is given as 0.25. Na is just calculated as 490. So Fa equals to mu s into Na. It is going to be equals to 0.25 into 490. So Fa is equals to 122.5 Newton. So once Fa has been calculated, now if you look at it here along the sigma y, you can basically calculate as Fa is being calculated. Now you can apply sigma Fx. If you apply sigma Fx, sum all the forces along the x-axis, sum all the forces, and your positive x direction is this one. Your positive y direction was this one. This was your positive y direction. This is your positive x direction. So when I sum along the x-axis, this is my positive t. Okay, this Fa is along the negative x, t minus Fa equal to 0. So what I can do is this minus Fa will go on the right hand side. So you can get Fa was 122.5 Newton. You put t equals to 122.5 Newton. Okay, so this is the tension. Okay, so this tension is basically, this tension has been calculated here. Okay, now basically this, and if you look at it, this was the sense of t was along this positive x. Okay, now when we go to block B or the crate B, what are going to be happen? We remember that we have calculated t as 122.5 Newton towards the positive x, Now you go to block B. See, when we go to block B, the sense changes. Okay, the sense changes. Okay, so it means that this t actually in equilibrium crate A was towards positive x, but now this t is towards negative x. So when we go for frames and machines, we will see that this is an internal reaction force. This t is the internal reaction force. Okay, so remember for crate A it was for crate A t was positive, and for crate B or crate A t was positive. If we sum it along the, this was our positive x. Okay, this was our positive x. So t was positive, and now the t is negative. Okay, so plus t minus t is 0, because actually if you look at it, there is no tension for, there is no t here. Okay, but so t is an internal reaction force that we have calculated it. Okay, so you must remember this way. In frames and machines also you will do the same. Okay, plus t minus t equal to 0. Okay, so very important concept. So once this concept is clearly understood, let's see this FPD. Try to understand this FPD. The normal direction will act downwards. This component, which component? This component is taking it on. This is the sense, it's going to taking the crate in this direction. So friction is in this direction, weight is acting downwards, and t is in towards the negative x. Simple, apply sigma fx equals to 0. So p cos 30 minus along the x-axis, again remember this is our positive x. So p cos 30 minus fb. Okay, and again there is this force which is on the negative x. Okay, this is our positive x. So p cos 30 minus fb minus t equals to 0. From here we know that fb, what was fb, is equals to mu s into nb. Okay, so we can apply this. So cos 30 is 0.866 t minus mu s is given as 0.25, nb minus t is calculated already just in the equilibrium crate A, it is 122.5. We call this as equation number 1. Now you apply we call it equation 1 because you have two unknowns. P is an unknown, nb is an unknown. Sigma fi equal to 0 if you apply. So you have this one more component is going to be produced. This is going to be this component. Okay, this component is what? This component is P sine 30. This component is P sine 30. Remember? Okay. So this is P sine 30 acting towards the positive y. What is going to happen to our NB? This is also acting towards positive y, and the weight is acting downwards. This is minus 490. So if you look at it again, you have got P and you have got NB here. So either you can solve it simultaneous equation as a, or you can, what you can do, from here you can calculate your NB. So NB will be equals to 490 minus 490 goes on the right hand side, plus 0.5 P goes on the right hand side. So this becomes your NB. You can put this NB after calculations. You can put this NB here. If you put it here, so you can say it is going to be 0.866p minus 0.25, 490 minus 0.5 minus 122.5 equal to 0. So once you have put it here in this equation, if you look at it, now basically if you look, this is an all equation is in P. So from this linear equation you can calculate the value of P. So P is equals to 247.2 Newton. Okay, so this P, what does this P tells us? This P which is calculators, it tells us that if you go, this is the maximum force. Okay, that maximum force P, this is going to be the maximum force P that can be applied without causing the 250 kg plates to move. Okay, so I hope you understand this type 2 problem. Okay, this type 2 problems are a bit trickier than your type 1 problems. So thank you very much.